So since I am not at 11:30, so on behalf of Department of Mathematics and my personal behalf, I would like to thank Professor Chelvam for giving such a nice, interesting lectures in a series. And in fact, when I decided to have the refresher course, immediately I contacted him because I was damn sure that the first yes I could hear from him. So and immediately within few minutes I received the message that yes, he will deliver a talk, and I asked, can you give a little more? So he said, you just name the number, I will do it accordingly. So I'm very much thankful to you, sir, for giving wonderful lectures in this refresher course. And sorry, I will not be available at 11:30, so please excuse me. With this request, I request you to deliver your talk.
Really, I enjoy this, sometimes, in fact, the refresher courses, sometimes it will be very complicated dynamics, one part of the program is on the statutory compulsions. The other part of the component is on the academic. But however, I enjoyed the audience and the program. Really, I am thankful to Professor Joshi for this nice opportunity. Only thing that I appeal to the participants, if you could get some collaboration or some work out of this, you are welcome, and you please record wherever you benefit out of an academic program. If you record, that will be the thanksgiving for the nice program which is being organized by Department of Mathematics, Pune University. Yes, so thank you. With this, let me start the last lecture. Okay, fine. Of course, as I was telling about this Cayley graphs, which was dealt for group theoretical sense for the past 3 lectures. Now, just I would like to give the Cayley graph of commutative rings. Of course, the very fundamental paper on this particular topic, the aim was characterization of automorphism groups of unitary Cayley graphs. In fact, there are very few papers on this, even the spectrum, the automorphism group and spectrum of Cayley graph, unitary Cayley graphs. And of course, the previous papers, they appeared basically on number theoretical properties, and ultimately things have come out. But in order to overcome certain difficulties in characterizing the automorphism groups of unitary Cayley graphs, this particular concept was introduced algebraically. They have been comfortably dealt upon. But I'm not going to touch upon that, lack of time, and I can give the reference. Interested people can go through and find things there. Of course, just I will be concentrating on these things. Cayley graph of commutative rings, generalized Cayley graphs, in fact, generalized unit and unitary Cayley graphs, how the things were progressing, what are their properties. And of course, at this point of time, my information to the participants is nothing but when we come to ring theory or the algebraic structure of commutative rings, there are 2 operations. One is addition, another one is multiplication. And with respect to addition, it is an abelian group. And another fact is this R plus, suppose I take it, throughout my lecture, R will denote the commutative ring with identity. Of course, identity is non-zero. And Z of R denotes the set of all zero divisors of R, which is one of the, what is that? One of the part which decides the structure of the ring. So set of all elements A, comma B in R such that AB is equal to 0. Of course, 0 is the universal annihilator. When I say something is an annihilator, A is an annihilator of B, when this property is being true, A is an annihilator of B and B is an annihilator of A. Of course, the 0 is a universal annihilator, and apart from that, there are elements with this property, and they decide the structure of the ring. And Z star of R denotes the set of all non-zero zero-divised sets of R. And there are some special types of zero-divised sets called nilpotent elements. An element A is said to be nilpotent if A power n is equal to 0, n is the least positive integer satisfying that property. Of course, it is to be noted that when A power n is equal to 0, naturally, this is the smallest positive integer. So A into A power n minus 1 equal to 0. Neither A is 0 nor A power n minus 1 is 0. So naturally, they are any non-zero nilpotent element is a zero divisor. And it is a subset of Z of R. Of course, according to binomial theorem, one can realize that sum of two nilpotent elements is again nilpotent. If A is nilpotent, A power m is equal to 0. If B is nilpotent, B power n is equal to 0. And one can have the expansion A plus B to the power m plus n, and which will be 0. Ultimately, the nilpotents form an ideal, whereas Z of R, the zero divisor set, is not closed under addition. Okay. Of course, the complementary of zero divisors in any commutative ring is called as regular. And people may know about the von Neumann regularity in the case of commutative rings, but that's not here. It is mere designating the complement of the zero divisor set in R as regular elements. Of course, a subset of regular elements is U of R. It's a set of all units. Naturally, they are the elements with multiplicative inverse. Of course, as I said just before, this when R is a ring, even non-commutative ring, R plus is an abelian group. And once you have a group, you can talk about the Cayley graph on this. And of course, now you can ask the question, when we talk about the Cayley graph, naturally, we will be interested in the generating set as we have seen in the previous talk. But there is a very general graph constructed on any commutative ring with respect to the subset of an R. So that is the starting point of Cayley graph of commutative rings. Of course, Akhtar in 2009, they have defined the unitary Cayley graph of a commutative ring. Of course, this particular aspect mentioned in point number 1, there are two graphs. One is there is a difference here. You please look at that. So there are two kinds of graphs with respect to ring. One is Cayley graph of R with respect to some subset, in the sense just we were talking about in the case of groups. Another graph is Cayley plus. Just I will come to the definition little bit, just little while. And of course, Ashrafi et al., they have defined the unit graph of a commutative ring, and it is also Cayley plus of R comma U of. Or at this point, I would like to mention that in the case of a ring R, there are two classes of graph constructions. One is using multiplication. Another one is using addition. And please recall that there is a graph called the zero divisor graph of R, in which the vertex set is Z star of R, non-zero zero divisors of R, and the edge set corresponding to the relation that two distinct wedges are adjacent if their product is C. Please recall that for a given commutative ring R, the zero divisor graph of R is nothing but the simple undirected graph with vertex set non-zero zero divisors, and the edges are created according to the condition that if the product of two distinct elements is 0, then they are adjacent. So here the algebraic condition is product is 0. On the other hand, there are graphs which are defined using addition. In fact, in the sense of ring theory, these classes of graphs, they come under this umbrella of Cayley or generalized Cayley graph. In fact, there is a most general situation, and that I will give it fine. So that is what I'm mainly concerned about. Okay. In fact, let me give very few definitions of graphs constructed from rings. Of course, I just told you zero divisor graph. That is the first ever graph construction from a commutative ring. Of course, it was by Ivan Beck in 1988, an Italian mathematician. The paper appeared in Journal of Algebra. Of course, people may wonder that the title of the paper was, it is not anything representing graph theoretically. It is the title of the paper is on coloring of rings. So they have constructed a graph and they wanted to find the chromatic number. Of course, it was Beck conjecture that the chromatic number is equal to the number of minimal prime angles. And in 2005, Electronic Journal of Combinatorics, Fuchs et al., they have only given this general framework. Let R be a commutative ring. Let me consider C a subset of R with C is equal to minus C. Minus C is nothing but set of all minus A in C. Of course, when the group is abelian, naturally we used to write addition. That's a convention, addition. And thereby, when I take C, naturally I can find additive inverses of elements in C. That is what we call it as minus C. And as in the case of group theory, the C is equal to minus C means it is a symmetric property. So the condition 2, which we have stipulated on the generating set of the Cayley graph, is supposed to be the C is equal to minus C here. And of course, when you have a C is equal to minus C, the Cayley graph is nothing but this way, Cayley R comma C. It's a graph with the vertex set R, and the edge set is a set of all xy. Xy is edge such that x not equal to y, and x minus y is in C, x comma y in R. So this is what general situation. And can anyone say, in the perception of the Cayley graph of a finite group and this definition for a commutative ring, what I am not considering here? Please note that finiteness is there. I don't mean finite. Okay, even for a finite commutative ring. When we compare this definition with the definition of the Cayley graph of a finite group or Cayley graph of a group, literally what we are not considering here, but considered the
generating set.
Generating set, literally. I'm not bothered about the generating relation because it's just a subset I'm taking. And can you foresee what will be the consequential impact on the graph when I drop the requirement of generating set from the definition? Graph theoretically, what shall be the impact? Can you foresee?
Maybe it is connected.
The graph need not be connected. When it is a generating set, when this C is a generating set, naturally this graph will be connected. When it is not a generating set, there is no necessity that the graph is connected. So ultimately, the one particular problem is, once you define a graph of this kind, naturally people will be interested in finding when it is connected. Of course, this is a standard one, just for the reference given. And this definition is in the general sense. That's what we have been talking about when I take a very general subset C, symmetric subset C, and this is a very general situation. In fact, recently we have made 3 papers on a particular topic. Even in the case of groups, we have done square sum graph. It's not our definition. It is a definition by Bengali authors Sen et al. And a cubic sum, prime sum graph, these 3 graphs we have defined on a finite abelian group, gamma be a finite abelian group. So gamma is a vector set naturally. In this case, 2 vertices are adjacent provided this for some t in gamma. What I call it as a square sum means, in fact, this definition was first considered for rings as a square graph. We have just modified that, or we have taken the group theoretical version in the sense that when group is abelian, naturally the power becomes multiple. So we take a finite group, 2 elements are adjacent provided a plus b is equal to 2t, which is non-zero for some t in gamma. Of course, this we called as square sum graph. We have more particularly studied about the complement of this graph, and the paper appeared in Houston Journal of Mathematics 2021, volume 1. That is first thing. And having done for 2, our natural concern was why not we consider for 3? This we call it as gamma a plus b is equal to 3t, which is non-zero for some t in gamma. That we call it as cubic sum graph. And the paper appeared in AKC Journal of International Journal of Graphs and Combinatorics 2021. Having studied about 2 and 3, naturally our attention was, what about the prime sum? Again, not equal to 0 for some prime number for some t in gamma. This we have studied about. Of course, the paper is under communication. And the things are very complicated. You cannot just like that, the proofs working for 2, 3, when it goes to prime, it's very complicated in the sense that so many cases of enumeration we wanted to consider. So several cases comes into the proof goes on a little bit boring. However, I feel that personally, instead of dealing 2, 3, p square, pq square, and so on and so forth, it would be nice if some structural properties arrived for these things. That is possible in the perception that this C, some subset C, this one. Okay. In fact, all these graphs comes under this natural definition C, because you know, in the case of square sum graph, this C is 2 multiple. In the case of cubic graph, this C is 3 multiple. So you can take P multiple and you can take any subset and do it. That's what this one. Fine. Okay. Of course, as I mentioned, the generating set is not considered. Ashrafi et al. In 2010 defined a graph called Cayley sum graph, appeared in Communications and Algebra. Let R be a commutative ring, C is a subset of R. In fact, you please note that here even C is equal to minus C is not assumed. This is a most general situation. The Cayley sum graph, Cayley, this that sum. R comma C is a graph with the vertex set R and two distinct vertices are adjacent provided X plus C is an element of C, X comma Y in R. And literally what is the difference? Instead of X minus Y in the case of Cayley graph, here X plus Y is taken. This is the only difference. And of course, certain generalizations took place, namely, I am not expecting generating set. I am not stipulating any condition on the generating set, condition on the set under consideration. So this is the most general situation. Of course, that's what just now I told you, the difference in the adjacency relation. Of course, this is the Z5 with respect to 1, 2 on Cayley sum graph. So any two vertices are adjacent provided the sum is 1 plus 0, 1, 0 plus 2, 2 plus 4, 1. In the case of Z5, this is 2. And by this time, naturally, one will be realizing the difference between the Cayley sum graph and Cayley graph. Structurally, what is the difference? Cayley graph and Cayley sum graph.
So cycle and here paths.
Structurally, I am asking. Cayley graphs are regular. Here it is not so. In fact, at the first instance, when I started my work on this, I was under the impression that since there is a one-to-one correspondence between these two elements in a group, for every y minus y is unique. Once you have x minus y, naturally x plus y is a one-to-one relation. Even I was under the wrong impression that the graph defined with respect to addition shall be isomorphic to this one. But very unfortunately or fortunately that this graph is entirely different from the Cayley graph. Of course, the Cayley sum graph is not regular. So that is. Again, Ashrafi et al. In 2010, they have defined the graph, unit graph. In fact, it is a particular case of a Cayley sum graph. The unit graph G of R equal to R comma E, where the vertex set is R, and two distinct vertices am I not visible?
Sir,
You are
that
visible,
is
sir.
for
Some participants are
participants, sir.
What?
that instruction for participants are not for some participants are video off.
Okay.
So that is
Oh, it's okay. It is a general message.
yes.
Yeah, general, sir. Yes, sir.
The unit graph is a particular case of the Cayley graph, or I can put it in one word that the C is the units of R, then that graph is unit graph. So vertex set is R, X plus Y in U of R, that is called the unit graph. The unit graph is denoted by G of R. And here is a graph on the integers of, and this is a unit graph. Of course, this is an infinite path. Willfully, I have taken this because of the reason that when I say graphs considered corresponding to commutative rings, one must realize that I am not considering only finite case. The infinite cases are also comes into the picture. So this part of the graph theory talks about infinite graphs also. Of course, you can see in the case of integers -1 and 1 are the units. The alternative elements you can just add and see that it is either -1 or +1. And in this sequence, in 2008, Anderson and Badavi, they have defined a graph called the total graph. And the total graph is T gamma of R. Perhaps Asir might have given this definition, or I don't know what is the content covered by
It's
Asir.
given, sir.
Vertex set is R, and two distinct vertices are adjacent provided X plus Y in ZFR. Now look at these things. R, zero divisor set, U of R. Now when R is finite, you can see that can anyone see the proof for this one? A very finite commutative ring, any element is either zero divisor or unit. Sorry, just a minute. I will come for 1 minute. Sorry for the. In the case of finite commutative ring, every element is either zero divisor or unit. It's a very simple fact. Of course, one can see the proof. Can you state the famous theorem for this, which you come across in the ring theory? Can anyone say? Suppose I say this. If A is an element of R, if A is not in zero divisor set, then I have to prove A is a unit. Am I correct?
You look at the all multiples of A.
Yeah,
And
there is a famous theorem in ring theory. That's what I'm asking about. Every finite integral domain is a
field.
That's what I'm going to use of. When I say A is not in ZFR, my domain, my path goes to integral domain. R is already finite. That's what you said about you take the multiples, they are all distinct, and you will get our identity there, and ultimately A has got an inverse. So that is the proof. So in the case of a finite commutative ring, every element is either this one or this one. Okay. So R is finite. I am considering graphs with respect to both Z of R and U of R. Okay, fine. That's what our one is total, another one is unit. but the same adjacency algebraic condition, namely x plus y is this. Okay. Of course, as a passing remark, I would like to mention that in the case of zero divisors, multiplication used as a tool to define adjacency. In the case of total, addition is used. You can see the simple one. This is the graph, total graph of Z4. The elements are 0, 1, 2, 3. Of course, zero divisors are 0 and 2. If you add these two, please note that this graph is disconnected. Willfully, I have drawn this way. It is only 2K2. So the total graph may be disconnected. However, there are instances in which it is connected. The total graph of Z6, this one. And yeah, okay, fine. You can see what are the zero divisors in C6, and you can, if you add any two element, it will be there. Fine. And one of the important algebraically important fact is the set of all zero divisors is not closed with respect to addition. Can anyone give an example for this? Zero divisors of the set is not closed under addition.
2, 3 in Z6.
Pardon?
2 and 3 in Z6.
2 and 3 in Z6. 2 plus 3 is 5. It's not a zero divisor because 5 is relatively prime to 6. Okay, if it closed under addition, what happens ultimately algebraically? Suppose you take Z of R as a subset of R. It enjoys all properties required for an ideal except closure of addition in general. You know what are the conditions for a subset to be an ideal? With respect to addition, it is a subgroup. With respect to multiplication, left multiplication, right multiplication, because we consider here one of the part is enough. So once if Z of R is closed with respect to addition, naturally it is an ideal. Okay. When it is an ideal, it is a prime ideal. Why? When Z of R is an ideal, it is happen to be prime ideal. Why? For example, there are two sets in ring, annihilator of A, which is equal to set of all x such that Ax equal to 0. And of course, the annihilator of A is an ideal of R. And this zero divisor is nothing but a union of these annihilator ideals. And not only, of course, this A should not be 0 because annihilator of 0 is R. And not only that, this Z of R is union of prime ideals in R. P is prime. So what happens now? Z of R is union of prime ideals, P is prime. When union of certain ideals is an ideal, what will happen? For example, right hand side, you assume that there are three prime ideals, P1, P2, P3. When P1, P2, P3 are prime ideals and their union is an ideal, means what will happen ultimately? What will happen ultimately?
You will just have one prime ideal.
It is one prime. Why? The reason is, suppose P1, P2 is an ideal, if and only if union of two ideals is an ideal, if and only if one of them is contained the other. So either it will be P2 or P1. You can extend this. Ultimately, the union of prime ideals is an ideal, then naturally it is only one. Thereby it is a prime ideal. Once it is a prime ideal, the quotient becomes integral domain. What is the quotient? R by Z of R. When R is finite, finite integral domain is a field, thereby R by Z of R is a field. When R by M is a field, M is a maximal ideal. Therefore, Z of R is the maximal ideal. All ideals are subset of Z of R. Therefore, Z of R is the unique maximal ideal. Ultimately, any ring with unique maximal ideal is nothing but local. It's a local. So a ring is said to be local if it has unique maximal ideal. So when R is finite and Z of R is an ideal, that ring becomes local ring with maximal ideal. Yeah. Okay. Now just please look at that. This is a unit graph that is nothing but Cayley plus of R comma U. When R is finite, just now we have observed. This is what the relation between these two. Sorry. This is complement of the total graph. This is complement of the total graph. This is unit graph. This is Cayley sum graph. They are one and the same. No. Sorry. So in that sense, this complement of the total graph and the unit graph and the Cayley sum graph are one and the same when that subset C is U. Okay, fine. That's there. Okay, these things we out. Another graph by name comaximal. Why I am giving so much of various things is nothing but one particular concept when it comes to ring theory, because of the varied properties of element-wise structure and the substructure, the things are getting enlarged. It's by Maimoni et al. The graph is comaximal graph. It is denoted by CFR. And again, the vertex set is R. Two distinct vertices are adjacent provided the condition is Rx plus Ry is equal to R. Suppose R is a commutative ring and X is an element of R. Can anyone say what is Rx? Set of all multiples of R into X.
Ideal.
R is an element of R. What is this structurally?
Ideal.
It is only ideal or something more?
Ideal
Ideal,
generated by X.
Principal ideal.
Principal ideal.
Ideal generated by X. Of course, when you go for generalization, R is a commutative ring with identity. R is a general ring. This is not the case. The things are entirely different. So, okay, fine. So literally, this is nothing but ideal generated by X plus ideal generated by Y equal to R, which is in the sense they are co-prime ideals. That is why co-maximal co-prime ideals. Okay. And of course, this is the co-maximal graph of Z6. Z6 is 0, 1, 2, 3, 4, 5. And naturally, the ideal generated by 1 is full Z6. Ideal generated by 5 is Z6. The others are there. And when you take an ideal I and plus R is always R, therefore, this ideal generated by 1 plus whatever thing you put it, you will get only R. Therefore, this is the full vertex. This is a full vertex in the sense that it is of degree cardinality of vertex at -1. For other things, you can verify. And carefully, if you look at that, yes. In most of the cases, the graph is either regular or biregular in the sense that the degree is either some k or k-1. But in this case, it is not so. There are vertices of degree 5, degree 3, degree 4. So it's a general situation. Now let me have a look at the two graphs. One is unit graph, another one is co-maximal graph. In G of R, the adjacency relation is x plus y is an element of U, and in C of R, Rx plus Ry is equal to R. Okay. Now I wanted to compare these two graphs. Both the graphs have got the vertex set same R. Only if at all there is a difference, it is with respect to edges only. More specifically, my claim is this unit graph is a subgraph of co-maximal graph. So naturally, what I must prove, every edge in the unit graph is an edge in the co-maximal graph. That's why I take xy is an element of the edge set of the unit graph. By definition, x plus y is a unit in U of R. So once U is a unit, U inverse exists, you can multiply. And you multiply throughout by R. R into U inverse of x plus R into U inverse of y is equal to R. So that is, this can be made as Rx plus Ry is equal to R. Ultimately, this xy is an edge in co-maximal graph. So the unit graph is a subgraph of the co-maximal graph. Okay, all these things, there is a generalization takes place with respect to some particular type of subsets called multiplicative prime subsets. A subset of a ring is said to be multiplicative prime subset. So naturally, both the terms should be meaningful. When I say multiplicative, the subset is closed under multiplication. That's what being designated as AB is an element of H for every A in H and B in R. And it is a prime in the sense that AB in H implies either A in H or B in H. So this multiplicative prime subsets, you can take examples that every prime ideal is a multiplicative prime subset. Union of prime ideals is a multiplicative prime subset. Of course, Z of R is a multiplicative prime subset. Not only Z of R, the complement of Z of R is also multiplicative prime subset. People may wonder what is the difference here, both the things same. Am I correct? I have written the same thing in two ways. Am I correct or I'm wrong? H is equal to Z of R and H is equal to R minus Z of R, U of R, they are one and the same. Am I correct?
Yes. Finite.
Finite case only. So in the case of infinite, they completely different. They are different. That's why, of course, in the case of infinite, which one is a bigger set? This one is a bigger set. here there are elements regular, which are units, and there are elements which are regular, which are not units. Okay. Journal of Algebra Applications, Badavi again in 2013, they defined a graph called generalized total graph. So generalized total graph is rendered by GTH of R, for which the vertex set is R and the two distinct vertices are adjacent, provided X plus Y is an element of H. So you please see the multiplicative prime subset has got so many possibilities with respect to prime ideal, with respect to union of prime ideals. This one, of course, this is what the total. In the total graph, if addition of two elements is a zero divisor, they are adjacent. But whereas in the generalized total graph, this addition could be either in a prime ideal or union of prime ideals, or it is complement of the units regularly. Sorry, complement of the units. So it is a general situation. The total graph, generalized total graph, defines this one. Of course, what is this is what just I observed that if H is equal to Z of R, the generalized total graph is nothing but total graph. And these two share many properties, that's naturally. One of the fundamental things is nothing but when R is an integral domain, there are no zero divisors except 0. So in the case of integral domain, what shall be this? Can anyone say? Structurally, what shall be this? R is an integral domain. The adjacency is nothing but X plus Y is a zero divisor. X and Y are, of course, distinct. So, what shall be this one? Can anyone
K2, copies of K2.
Only K2? What do you mean by K2? What he means is that X is there, minus X is there. Naturally, the sum is 0, which is a zero divisor in the integral domain. Therefore, what he feels is a union of K2. My question is the situation everywhere?
No, if characteristic is 2, then this won't be the situation.
No, I don't go for characteristic 2. In that case, 2x equal to 0 for all x.
Yeah, x equals to 0, then you will have a...
But my question is, does it the case always x and minus x this way? There may be some elements for which this may occur. For some elements, x and minus x different. For some elements, x equal to minus x. Both the things can appear in a commutative ring simultaneously. So in the case, what shall be the difference in the structure of the total graph? If R is an integral domain, then total graph of R is nothing but union of K2, then union of
Loops.
Okay. The second part is corresponding to elements with the self-additive inverses. The first part is corresponding to elements which are with distinct inverses, additive inverses. So it is a very trivial case in the case of the total graph. But in the case of a generalized total graph, this is something different. Of course, I will come that later on. In fact, we have studied about, even for the case of the fields, we have studied the generalized total graph of fields, which appeared in 2019. Okay. With all these things in our hand, A very beautiful and clever definition by Cayley et al. Acta Mathematica Angelica in 2012. They have given a very generalized frame for this purpose. The generalized graph is this. But very unfortunately, they couldn't name the graph because it is an umbrella which accommodates almost all the graphs just we have been looking at. Let G be a multiplicative group of U of R. Suppose S is a non-empty subset of G and which enjoys symmetric property, namely S inverse equal to S inverse S in S, which is same as this is equal to S. Sorry. Okay. Fine. And we define a graph gamma RGS. So what are the inputs here? R is a commutative ring with identity. G is a subgroup of the multiplicative group of units of R. S is a symmetric subset of G. Fine. We define a graph which is rendered by gamma RGS, which is a simple graph with a vertex at R. And the two distinct vertices X and Y are adjacent, provided there exists a S in S such that X plus Sy is an element of G. See, this is what the very general situation. X plus Sy is an element of G. And they have not named this graph. This is a graph construction from a commutative ring, something they have put it, the title of the paper. Okay. Suppose in this definition, if you put S is equal to 1, if your symmetric subset contains 1, what will happen? If S is equal to the singleton 1, then this definition is nothing but this becomes X plus Y is an element of G. G is a subset of U of R. Ultimately, X plus Y is an element of U of R. Therefore, this when S is equal to 1, gamma RGS is nothing but the unit graph G of R. So one class is a subclass of this one. When S is equal to 1 and R is equal to finite, the unit graph is complement of the total graph. When S is equal to 1, R is infinite, then unit graph is a subgraph of the total graph. Sorry, complement of the total graph. When S is equal to -1, the adjacency relation becomes there X plus Sy. When I take S is equal to -1, X minus Y is an element of unit. Ultimately, it is a unitary Cayley graph. So unit graph is a subgraph of this class. Unitary Cayley graphs are elements of this class. So in one stroke, they have made almost all the graphs a member of this class. Of course, Ramanujan having defined this definition, they have obtained some properties. Especially, they have got characterizations for the graph to be complete and planar. Of course, this is a very important class. A graph is said to be Artinian if it satisfies descending chain condition. Descending chain condition on ideals. That is, if you start with one particular ring, if you go on decreasing the size of the ideal, it will terminate at a finite point. For example, I will give the complementary case. In the case of integers, is it true? Am I correct? Is there any doubt? Of course, the first one is set of all 2 multiples. This is set of all 4 multiples. Naturally, is it not? So this is, I am decreasing the size of the ideals. My question is where it will terminate. If I go, when it will get terminated. What does it mean, terminated?
It will not.
I will get a stage wherein something comes here and the same comes in the next stage. So thereafter, I may not be able to proceed at all. My process of decreasing won't work after a certain stage. That is called termination at a particular point. Can you tell me at what point this decreasing sequence of ideals get terminated or stationary? That is called stationary. When?
It will never terminate.
So this is not Artinian. A ring is said to be Artinian if every decreasing sequence of ideals is finite and it is stationary. On the other hand, a ring is said to be Noetherian if the ascending sequence of ideals gets terminated. Is the ring of integers Noetherian? It is not Artinian because I have given a sequence of ideals which goes on decreasing because it is only 2 square, 2 cube, 2 power n, 2 power n plus 1, so on and so forth. It's never ending process. On the other hand, when I go on increasing, I should get termination. That is called Noetherian. My question is whether the ring of integers is Noetherian or not.
Yes, it is Noetherian.
When,
So,
where it will terminate?
In a maximal ideal generally. Maximal ideal. So ideal generated by prime number.
Prime number. In fact, you are stopping at a non-trivial point. At the next, what is the next term? Okay, fine. What he is talking about is correct. Suppose I take an ideal. I goes on increasing. Where it will end up? What he says is, sir, it will end up at a prime number P, which is a maximal ideal in Z. My question is, even beyond that, what will happen?
You will have whole ring. So next point will be whole ring.
So whatever be the sequence of increasing things, this is a prime factor, next factor is 1, therefore it is generated by 1, that is nothing but. So Z is Noetherian, Z is Noetherian, but not Artinian. And what is the benefit? In fact, why I am, just for the sake of information, I tell you, the research in this domain of graphs from commutative rings considers this way. When I take R, the first thing is R is finite case. Second thing is R is local. In the sense that Z of R is a maximal ideal. So all along, what I am interested is, this is my consideration. I wanted to know what it is, whether it is known to me or not. Yes, it is a unique maximal ideal in this case. The next consideration is R is Artinian. What is the benefit of Artinian? There is a structure theorem called Artinian commutative ring is the any Artinian commutative ring is direct product of Artinian local rings. Every Artinian ring is the direct product of Artinian local rings. So what do you mean by Artinian local ring? It's a local ring means this R1 comma, there is a maximal ideal M1, or in general for each I, it is Artinian local ring means Ri comma Mi. So M1 is a maximal ideal in R1, M2 is the maximal ideal in R2, Mk is the maximal ideal in Rk. So when R is equal to R1 times etc. Rk, and each one is a local ring, can anyone say what it is? I wanted to know about the zero divised sets of R. Can anyone say what it is? For the sake of simplicity, let me take the simple case of direct product of two local rings. My question is, what is this?
From first ring,
Hmm.
you take zero divisors.
First, what I should take?
From R1, you take all zero divisors.
What
in
it is
first
exactly?
component,
What it is exactly here?
Z of R1, element
what
of
is
Z of
exact-
R1.
Because it is local.
Yeah, local.
It's M1.
M1. Yeah,
Am I correct?
M1
R2
cross
and
R2
R2 cross M1. M2.
union R2 cross M. Sorry, R1 cross M.
So the benefit of Artinian decomposition for an Artinian ring gives you an explicit way of finding zero divised sets in R. This is a very sophisticated. Exactly known. I know what it is. But beyond this stage, nothing is known about Z of R. So it's a complicated domain with respect to any problem in algebraic graph theory of graphs from commutative rings. So it's things are complicated. Finite, local, Artinian, because until this moment of time, we know what is the zero, what are the zero divisors. Okay. Of course, that's why Ramanujan et al. They have considered the this gamma RGS in the case of Artinian ring, and the G is equal to U of R. Of course, Asir and myself, we have done some work on this gamma RGS in the sense of topological properties, namely genus. We have characterized, in fact, they have characterized for planar. Planar means genus 0. And we have done some characterization for genus 1 or 2. Of course, this paper appeared in Acta Mathematica Angelica. And this is in 2012, 2014, in 2016, Nagipur et al. They started about a particular case of gamma RGS, namely gamma R comma, you take G as the full multiplicative group U of R, the semantic subset S also as U of R. They have initiated a study on this class gamma R U U. It is one of the elements in this one. Of course, with this particular G and S, they obtained necessary sufficient condition for gamma to be Hamiltonian, as well as gamma contains a perfect matching. Just I will skip this part. Maybe Asir might have covered. Otherwise, my aim here is In the case of the total graph or even generalized total graph, the graph structure is very explicitly known. For example, even in the case of a commutative ring, this T gamma of R is union of certain complete graphs and union of certain complete bipartite graphs. So because of this, we have done a quite number of, we have studied about very extensively about this total graph. In fact, because of this structure theorem, similar structure theorem is valid for GTH of R. That's also proved in the paper. That also gives something, but there are very other open problems in this domain. The total graph almost is over. So just I skip that proof. Okay. Now we have started about this gamma R. They have studied some, in fact, Nagy-Pour et al. They have obtained Hamiltonian characterization and the existence of perfect matching. But we have started the other properties of this particular graph. Because R happened to be Artinian, it's a direct product of Artinian local rings. Let the number of components be Q. So this. So literally, what is this? R is isomorphic to R1 direct product, etc. RQ. We arrange the indices in such a way that because Mi is a local ring Ri, and ultimate this universal assumption of finiteness is there. In fact, every finite ring is Artinian ring. So the quotient ring is a field. Ri by Mi is a field, of course, for all I. So let me arrange the number of cardinality of each field. So I split the indices in such a way that first T components, the field is nothing but Z2. Rj by Mj is equal to 2 for 1 less than or equal to J less than or equal to T. And Rk by Mk is greater than 2 for T plus 1 less than or equal to K less than or equal to T plus S, which is equal to Q. So what I am doing is this. R is equal to R1 direct sum R2 direct sum etc. RQ. Each one is a local ring. Maximal ideals are there. Their quotients is a field. So this is R1 by M1. It is 2. So the field is Z2. So I arrange the indices in such a way that up to the point of T, R1, etc., RT, up to this point, the quotient is nothing but Z2, quotient field. Then thereafter, RT plus 1, etc., up to RQ, the number of elements in the quotient field is greater than 2. I arrange these indices. Of course, this made us comfortable to study about this gamma. Of course, this is the technique of tool. These index sets we have used in the proof, but I skip it for this proof. Okay. And what are the structural properties gamma R U? Of course, we have first proved that Journal of Algebra and Applications 2017. Gamma is the vertex disjoint union of 2 power T minus 1 connected components. What is T? T is nothing but number of quotient fields for which order is 2. So ultimately, we could prove that this is true. Of course, these things are very explicit about this one. When R is a direct product of finite local rings, then the following are true. Gamma, this is gamma. This is gamma. This gamma is nothing but 2 power t minus 1 complete bipartite graphs of component size cardinality of R by 2 power t. And the gamma is connected if and only if R satisfies either of these conditions. Either gamma, yes, for every I, this quotient field is at least 3. It is of cardinality at least 3, greater than 2. When R is equal to R1, only one component, and R1 by M1 is equal to 2. And when R1 by M1 is of cardinality 2, and it is greater than K for others. So only in these are the 3 possibilities the gamma is connected. Either for all components, the quotient field must be of cardinality greater than 2, or only one component with the quotient field Z2, and the first component is Z2, and for other components, it is greater than 2. Of course, this gamma is Eulerian if and only if R satisfies one of the following properties. Either cardinality of R is odd, or R is equal to R1 and R1 by M1 is of cardinality 2, and this alpha 1 is greater than or equal to 2. That alpha 1 is nothing but, you see, any local ring is of, suppose R is a local ring, the cardinality of the local ring is prime power. In this case, R1 is a local ring with the M1, and this because of R1 by M1 equal to 2, here the cardinality of R1 is nothing but 2 power alpha 1. That is what that alpha. This alpha 1 greater than or equal to 2, it is an exponent of the local ring. So this is Eulerian only when either cardinality of R is odd or R is equal to R1 and the quotient field is of cardinality 2 with alpha 1 greater than or equal to 2. And first component is quotient field Z2 with the exponent greater than or equal to 2, and other components greater than 2 for every K. And the last possibility is either R1 by M1 is of cardinality 2 with the exponent alpha 1 is equal to 1. Please look at that. Here it is greater than or equal to 2. The other possibility is here. Alpha 1 is equal to 1. And the other components, quotient fields are greater than 2. And Rk is not a field of even order for some K. And these are all the possibilities under which R is Eulerian. And the proof is a little bit complicated. That's why I'm not getting into the proof. But the proof technique ultimately stands on these indices and quotient fields. Of course, gamma is unicyclic. Unicyclic means it contains only one cycle. If and only if it is isomorphic either Z3 or Z4 or Z2 of X over ideal generated by X square. It is split. If and only if either R is a field or R is equal to R1 with cardinality of R1 by M1 is greater than 2. What is split? A graph is said to be split. The graph can be partitioned to 2 sets. One is independent, no pair of vertices adjacent. Another part is click, and there may be adjust between these two. A graph is said to be split. You can find one independent set and another click such that there are only edges between them. So that is called a split. We have done this characterization. And claw-free, claw means K13, complete bipartite graph with this star, this one, K13. So we have proved when it is claw-free, if it satisfies the following conditions. Either R is a field, or R is equal to Z2 to the power Q, K greater than or equal to 2, and R is equal to R1 direction Z2 to the power R, where R1 is either Z4 or Z2 of X over X square, and R is greater than or equal to 0. Of course, this is one of the remarkable properties of this class. It is weakly perfect. Weakly perfect means chromatic number is equal to the clique number. And weakly perfect and perfect means chromatic number equal to clique number, not only for the graph, for every induced subgraph. If it is true, it is perfect. Of course, it is a strong perfect conjecture. Perfect graph conjecture was there, and it was proved by Seymour et al. In 2002. Gamma is perfect if and only if this one. Okay, R is equal to R1 direct sum RQ, 1 less than or equal to Q less than or equal to 4, and Ri by Mi is greater than 2 for all I. So in either of these cases, this gamma happened to be perfect. Of course, Anukumar and myself, we have studied about the complement of this graph, gamma or UU. Of course, please recall that a graph G is there, complement means edges which are, pair of edges which are adjacent to gamma are not adjacent to gamma bar, and vice versa. So that is complement. And Anukumar and myself, we have studied some domination parameters in gamma or UU that appeared in Indian Journal of Pure and Applied Mathematics. And in the same year, we have proved we have studied about the intersection graph of gamma sets in this. So here I should mention something about. We know gamma. What is the dominating set? Dominating set means a set of reality gamma. Once you know the characterization to find the dominating sets, I can find all dominating sets in this graph gamma. And now I am going to construct a graph called the intersection graph of this one. Intersection graph, in fact, it is a very general class of graphs because every graph can be considered as an intersection graph. Intersection graph means for which the vertex set is all these sets, all gamma sets of this one, and any two distinct vertices are adjacent provided their intersection is non-empty. So always the intersection graph means the vertex set is a class of subsets, and intersection is or the adjacency is through the intersection of the non-empty intersection of the corresponding vertices. And of course, not only in this situation, we have studied wherever we could explore the domination parameters of any graph, we have ultimately studied about the intersection graph. Of course, for this graph is also, we have done the intersection graph of this one. And Balaban and myself, that appeared in Fellowmate 2020, we have studied the complement of the generalized total graph of Zn, where P is a prime median. So I said the generalized total graph could be defined with respect to primordial, union of primordial, complement of units, etc. And for this, of course, I can tell you a thing that this we have done even for Zn. Of course, for the complement also. The problem still is open even for this case. When I take union of two primordials, the generalized total graph with respect to union of two primordials, still it's open. It's not that we have not done anything. Of course, in the general situation, instead of Zn, in the general commutative ring R and a primordial, we have done something on the complement of the generalized total graph. Of course, we have done the complement of the generalized total graph of a field with respect to the trivial zero ideal. Of course, these things are some of the references. Okay. Let me stop at this stage. Any observation or anything you wanted to say?
Yes, Frozen.
Yeah, please.
That characterization for Artinian graph of genus 1 or 2, 1 and 2. Can we say all the toroidal graphs are that Artinian groups? Can we characterize like that?
You see, that's what a graph is said to be toroidal if the genus.
Yes.
Planar means genus 0.
0. Yeah.
Toroidal means genus 1.
Can be embedded in torus.
If you could characterize any graph for which the genus is 1. In fact, what we have done is we have characterized all finite commutative rings for which the total graph is toroidal.
Okay. Okay.
Not only toroidal, even generalization
For
when
genus
the
1.
2.
Oh.
2. But beyond that, the problem is, in fact, there is a problem how to draw the graph in the plane. That itself, how to make an embedding.
Okay.
Itself is a very, when you go for, you see,
but I think any graph of genus 1 is embedded in torus, sir.
No. It is distinct, disjoint. That's because what is the genus?
It's a crossing number of non-planarity.
Yeah, you take this one, the K5. Sorry. What are the things remains to be added?
1 and 3.
1 and 3. Okay.
1 and 4.
1 and 4. What else remains?
5 to 3.
Pardon?
5 to 3.
But you cannot draw without crossing.
Yes.
Isn't it?
Yeah.
So either if I draw this, it is crossing this. Either this way, it is crossing this. Therefore, so in such a situation, you treat this planar embedding. This is a graph drawn in the plane. As you treat this as a drawing in the unit sphere, this ball.
Yes.
Okay. Once a ball is drawn, let me have a hook here. You see, if people could see me, this is the, you take that, I have a hook. This I will draw via the hook, not through the surface.
Yes.
Above that. So there is a bridge, just over bridge. That is what the concept of genus.
Okay.
And once you know the graph is planar, it is there are no bridges needed. You have the embedding. When toroidal means compulsorily one bridge is necessary. So it's not an inclusive class. So planar is not considered to be toroidal. It's entirely different. So it's only distinct characterization for each of the genus. Any other question?
Sir, have the spectral properties of Cayley graphs of commutative rings been studied?
Yeah, in the original paper itself, there are some characterizations for Ramanujan graph.
Okay, no, for the groups, excuse me, so for the groups they have been studied.
It is for Zian. It is for Zian.
Okay.
So there are some characterizations for which n, the graph is unitary Cayley graph is Ramanujan. The largest eigenvalue is something like 2.
Okay.
So there is a class of graphs called Ramanujan graphs with respect to spectral property. And for the Cayley graph of finite commutative ring, especially on Xen, such a characterization is available.
Okay.
In fact, there is another paper by H.N. Ramaswamy and his students from University of Mysore, Electronic Journal of Combinatorics, 2009, in which they have made some characterization for unitary Cayley graph with respect to spectrum using number theoretical properties.
Okay. Okay. Thank you.
Anybody else?
Sir, in your first lecture, you talked about star graphs, and you said that there are many things to work in the star graphs. So could you please provide a few references about star graph?
I do one thing. I have made 2 things. Today, I will share the slide presentation of yesterday and today, and at least some 12 or 13 papers which are very vital or which are being covered in my talk. I will give all. RAR file and a set of references, PDF files, and the slide files. Both I will send it to Joshi. He will in turn continue. That I have made.
Okay, thank you, sir. Thank you, sir.
And for any doubt or anything, you are free to make a mail. Just you can type my name, you will get the mail ID. Or in the slide presentation, I think I have given the email ID. You are free to contact. Only thing, please introduce yourself. I am the participant of this program, and we wanted to do it, and definitely we can interact.
Okay,
fact,
thank you, sir.
I am for any such academic interaction. Anybody else? Okay, in the absence of any more questions,
so
I really enjoyed your company in the sense that because you are all interactive, and definitely it is enjoyable, and wish you all the best. And I hope that I could reach you to some extent to my that is level best. So wish you all the best.
So
opportunity to HRDC Pune University and the Department of Mathematics Pune University.
So on behalf of all the participants and the Department of Mathematics and also the UGC HRDC Center, I'd like to thank you very much for accepting our invitation and being here with us for this refresher course and delivering lectures on Cayley graphs of groups and also rings. So thank you very much, and looking forward to seeing you some other occasion.
Yeah, definitely.
Thank you very much.
Thank you, Professor.
We shall meet if possible on some other academic.
Yeah, sure.
Thank you. Wish you all the best.
Thank you, sir. Thanks.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.
Can you have a screenshot, somebody? I don't know. What to do it, I don't know.
Wait a minute. Let me contact our.
At least all the participants, you can switch on your video. Somebody still without video. Normally, what I used to do is I used to take a photograph from camera. So that's the smallest. That's the technology without any problem. But however, I wanted to have a snapshot. If anybody could do it, it will be better. You can send me thereafter.
Yes, sir. I will take photograph.
Yeah, please.
Sir, before this refresher, I don't know anything about. I was not knowing anything about graphs and zero divisor graphs, but now I got very interested in all these things.
Okay, fine.
So maybe can work, and I will share something with you if I work out something.
So in that case, I'm happy that somebody could attract towards the discipline.
Yes, sir. Yes.
In fact, for information, our book on graphs from rings, which is going to be published by Springer International, it shall be available in the month of December. Yeah, 540 pages monograph.
Okay.
That's the first monograph on this particular topic. So you are academically, you are free to contact, and if we could establish the academic contact, it's really
Yes, definitely, sir.
happy.
We'll
Thank you.
look forward for it. Thank you, sir.
Thank
Okay,
you.
I'm just
Arnav.
taking screenshot. Be ready. Thank you.
Thank you. Please pass on. Thank you.
Thank you.
Thank you.
See you all.
See you all.
Thank you, sir.